Welcome to Lesson 1 of Unit 2. In this unit, we're going to be talking about the derivative, so the basic rules for differentiation. But before we can get into the rules, we have to understand a little bit about what the derivative is and what it represents. So in this lesson, we'll talk about rates of change. We'll define average rate of change and instantaneous rate of change. We'll also determine or define the derivative of a function using the derivative notation, and estimate derivatives of a function at a point. So, average rate of change. This is just a formula. The average rate of change is essentially the slope of the line that connects points A and B. So we say the average rate of change of a function is the change in y values over the change in x values. So for instance, in this example, you can see we have a function in red, and in green is the line that connects 2 points. We'll call those points A and B, or x values of A and B. The difference between those x values is some change in x, delta x. F of A and F of B are y values, and the difference between them is the change in y. The slope of the green line is just the change in y over the change in x, and we call this the average rate of change of f from A to B. So in calculus, one of the things that we will oftentimes do is take a well-known concept, like the average rate of change, and apply a limit. So in our very, very first lesson, lesson 0.01, we saw that by making the change in x really, really small, the slope of that secant line, or the average rate of change as we're now defining, could be used to approximate the instantaneous rate of change. Okay? So we saw a formula similar to this, that the slope of the secant line, m sub sec, was equal to f of c plus delta x minus f of c over delta x. And that was just the difference in two y values over the change in x. The difference, the two y values were f of c and f of c plus some change in x. So now that we know about limits, we can use a limit and apply that to that idea, and we get the slope of the line tangent to the curve defined by f at c. And this is our definition of derivative. This is your textbook definition of derivative of f at c. We're applying the limit as delta x goes to 0. So this is that idea of making our 2 points get really close together, or making that change in x so small that it becomes negligible. So let's look at an example. Find the slope of the line tangent to the graph of x squared plus 1 at the point -1, 2. So we're going to use this formula to find the slope of the line at c in this case being -1. So we plug in c plus delta x to my function, so c plus delta x squared plus 1, minus the function at c. And then we do a little bit of arithmetic to simplify. And notice that there is a delta x in all of the terms. And so delta x can actually cancel from the denominator. And I'm left with the limit as delta x approaches 0 of 2c plus delta x. But the limit as delta x approaches 0 yields just 2c. And we said that we wanted to find the slope of the line tangent to the graph at -1, 2. So the value of x that we're approximating or finding the derivative, or the line tangent to the curve, is -1. So we plug in -1 to get that the slope is -2. And you can see that here graphically. I've graphed in red the function x squared plus 1, and the blue line is a line that has a slope of -2, and it's tangent to the curve at -1, 2. So the derivative of f at x is defined as f prime. That's what this notation is read as, f prime of x, being equal to the limit of, as delta x approaches 0, of f of x plus delta x minus f of x over delta x. So the only thing that's changing here is instead of finding the derivative of f at a specific point, I'm finding just the derivative of f as a function. So what this formula should yield is a function of x, f prime of x, that would let me plug in any value of x to find the slope of the line tangent to the curve at that value of x. Okay. Just a note, there are a lot of different ways that the derivative is expressed notationally. So from left to right, we have f prime of x. We have dy dx. We have y prime. We have the derivative with respect to x of f of x. And this one is not used as much in our class, but in higher level mathematics classes like multivariable calculus, where you're taking the derivative of a function with respect to multiple variables multiple times, this would be read as the derivative of x, the derivative of y with respect to x first. Okay, so we won't see this last notation in this class very often, if ever, but do be familiar with the other four. Okay, so let's look at an example. We want to write the equation of f prime of x given that f of x is the square root of x. Okay, so we're going to start with my formula or my definition of derivative. We're going to plug in our values. X plus delta x goes into the function f of x. And in this case, we have a function or a rational expression that's more challenging to simplify. But one of our strategies that we can use from algebra is multiplying by the conjugate. And that tool is really useful because in the numerator, you'll now see that we have a sort of factored form of a difference of squares, namely a minus b times a plus b. And multiplied together, that should just yield a squared minus b squared, or the difference of squares. In the denominator, we actually won't distribute that delta x because we are hoping that delta x will cancel out with something in the numerator. And after a little bit of algebra, we see that only delta x is left in the numerator, and so those can cancel. And then applying my limit, as delta x goes to 0, I get 1 over 2 square roots of x. So this would be my function f prime, which is the derivative of the square root of x. So now that we have a function, we could plug any value of x into that function to evaluate the slope of the line tangent to the curve at that value of x. For instance, we could evaluate f prime of 9 by simply plugging 9 into the function that we found in part A. And we get 1/6. Okay. Another formula that you may see, and we'll definitely see in the next lesson, is the limit as x approaches a of f of x minus a over x minus a. In this formula, it's very similar to the definition of derivative. It's still a difference quotient. If you participated in the difference quotients activity, we have a difference in y values divided by a difference in x values, and the limit is used to make the distance between the x values go to 0. So instead of saying delta x goes to 0, we're saying we're letting x get closer to a. So still that difference between the two x values is becoming so small that it becomes negligible. So in summary, we have the instantaneous rate of change that we've defined can be calculated by taking smaller and smaller sizes of delta x from the slope of a secant line. Applying a limit to that secant line formula yields what we know of as the definition of derivative. Thanks for watching, and I'll see you in the next video.